Hi, welcome to the logarithmic function. We've just recently found a very big need for using this function in solving exponential equations, and here's some here with base e and then base 10, and using the idea of the logarithm of a number enables us to solve for the power. So the powers up here become easier to find using the notion of logarithms. And if you remember, we defined the logarithm of a number as the power required to raise the base to get that number. And now what we want to do is actually to treat the log function, either y equals ln x or y equals log x, base 10 there, as a function of its own right, and maybe to draw a graph and talk about its domain and range. So let's have a look at some history there. And John Napier was responsible for a lot of the work here, and he developed the word from two Greek words, logos meaning ratio and arithmos meaning number. So he developed a lot of ideas with logarithms which made big calculations a lot easier, and then it built on with other people. Just reading this here, you can pause the presentation and read that. This is a screen clipping from Pearson's, which we're using again this time, and it would be good to have a copy of that to check it out as we go. So it was also the basis of the slide rule. Just to give you an idea there of, let's say we were trying to do some very big difficult multiplications, something like 327.9, multiplying those two together. Can you see that if we converted them to logs and said the log of 372,432 plus the log of this would give us the log of the answer, wouldn't it? If we took, so this has some answer we want, and we could find the log of the answer by taking the log of each of these. So we'd be adding the powers here. So that's going to be easier than doing this long multiplication. So if we could change this to a power of 10 and just work with that power, and this one is a power of 10, we can add those powers of 10 to get the final power of the answer. So it made long multiplications and divisions particularly a lot easier to do, and helped science in a big way. There weren't electronic calculators then. So by encoding everything as powers of 10, made it a lot easier to work with large numbers. Alright, so that's where logarithm came from. Now let's see what further advancements we can make with it. So definition of a logarithmic function, we've said from exponentials. When we raise b to the x, looking at an exponential function, we prefer to have b as a positive, because get in all sorts of trouble if b is a negative. And if b is 1, we're saying b is not 1 here. If b is just 1, it's just 1 for every power, it's just 1. So here what we're going to do is say, well, let's define the log function as y equals log to the base b of x. And b, so far we've used is base e, or we've used b as base 10. And so therefore, if we have that, we can interpret that in an exponential way by saying if y is the log of something, log to the base b of x, then y is what? Log is a power. So y is the power you raise b to get x. That's from our fundamental definition, because the log of a number equals the power required to produce a number from the base, to produce the number for a given base. So when we say something is the log of something else, it means that's the power needed of the base to get that number. Okay, so if you look at trying to give a domain to a logarithmic function, then you're trying to raise b to some power. Okay, and if b is a positive base, when you raise it to any power, which we call the log, you will always get a positive answer. So you actually can't find the log of a negative number, because the base b will be positive from our exponential functions, and when we raise it to any power, it will produce a positive. So here, the only number we can put in place of x there is a positive number. You can only find the log of a positive number. So that's going to restrict the domain. But then, of course, you could have any value for that power. So y is a member of R, because you can have negative powers, 0 for a power, positive powers, irrational numbers as powers. We discussed that before. So we're now going to look at this function in its own right and look at its graph and that sort of thing. Okay, so let's come down here and look at its graph now. So this is the graph of b to the x down there. And then if we drew the graph of log to the base b of x, let's try and get this point here. What is log to the base b of the number 1? What power do you raise b to get 1? Well, if b is not 0, any power, or the 0 power of any base is 1. So e to the 0 is 1, 10 to the 0 is 1, and so on. So we have this point here at 1 0. And then we might also realise that if we have log to the base b of b, what power do you raise b to get b? It's the power 1. So another point that's always going to be on the log graph is to base b will be b1. So if you're using log to the base e on its graph, you would always have the point e1. And on log to the base 10 of 10, we would have 10 1. Because remember, let's read this again. Y is the log of 10 to base 10 means what power do I raise 10 to get itself? It's just 1. So that gives you an idea of the general nature of these two crucial points there. Now you might like to also think, well, hang on, that's interesting, because on the exponential function b to the x, b to the 0 always comes to 1. All the exponentials go through this point. It's also true that when x is 1 in the exponential function, b to the 1 is b. What do you think? We'll look at this again later, but it looks like b to the x, y equals b to the x, and y equals log to the base b of x are what? Inverses. It looks like one's a reflection of the other in the line y is equal to x. So we're going to investigate that later on, where are they the inverse of each other? Certainly looks that way. Let's go down and have a look at some logarithmic expressions and equations and so on. So you can actually write a log equation or log expression. You could say log to the base 2 of 8 is 3, because what power do you raise 2 to get 8? It's the power 3. So just using our basic definition. Or you could check it out, making it an exponential equation or statement. 2 to the 3 is 8. Okay, so it's important to be able to go back, as Pearson says here, from a logarithmic function into an exponential, a logarithmic equation to an exponential equation backwards and forwards. So as long as you're using the same base, you can quickly move from one to the other, because the log of a number to any base is the power of that base required to get the number. So let's always remember log is equivalent to a power or exponent. It's a power of some base. Let's go down and develop it a bit more now. And so here we are. Here's some rules. Logarithmic equation would be y is the log to the base b of x. And what's equivalent to that? Well, of course, these are equivalent, because if y is the log to the base b, what does that mean? Y is the power of b required to get the number. So really, these are alternative definitions of that relationship. So let's try to formalise it a bit now. If b is a positive base, and it's not 1, because 1 to any power is just 1, then log to the base b of 1, log to the base b of 1 is 0, because 0 is the power you raise b to get 1. Log to the base b of b itself is 1, because 1 is the power you raise b to get b. Log to the base b of b to the x. What power do you raise b to get this? Well, the thing's already written as a power of b. And so it is just x, because b to the x is equal to b to the x. Well, what we're saying here is if something is written as a power of the base, let's check it out. What's log to the base b of b squared? Well, from our definition, log to base b says what power do you raise b to get this expression? What power? Well, it's already written as a power. So it is just that power itself. What about, so these are fundamental algebraic statements, these last two, of our word definition. And that is, here's our word definition here. Log to the base b of x is a power to which b must be raised to get x. So they're saying it the same way. We're raising b to, what's this? Log to the base b of x. That says by definition the power you raise b to get it. So you must get x as a result of raising b to that required power, log to the base b of x. So the IB love using these definitions in algebraic form, and they're not hard, so we're going to try and get our head around those in this presentation. But let's go down and have a look at some examples. So here's example 9, we'll just come back a bit. Find the value of each of these logarithms, and let's have a look. So we can say then, what is log to the base 7 of 49? Well, you can write 7 to the y is 49 and go through that. I'd rather you say, well, y is log to the base 7 of 49 implies y is log to the base 7 of 7 squared. Oh, so that's just, what does it say? The log to the base 7 is a power I need to raise 7 to get this one, so it's just 2. Okay, and then over here, log to the base 5 of a fifth. Let's write a fifth as a power of 5. And then it's obvious what the answer is. Y is the log, it's a power needed to raise 5 to get the number. The number is already written as a power of 5, so it's just neg 1 from our definition, and so on. Log to the base 6 of root 6. Well, let's write root 6 as a power of 6. It's 6 to the half. So this is saying find the power of 6 to get this number. It's written as a power of 6, so the answer is that power. Do you get the idea? Let's look at log to the base 4 of 64. Log to the base 4 of 64. I'm trying to write 64 as a power of 4. And is it? Well, I think it's 4 cubed. So therefore, what power is necessary to raise 4 to get this? It's already written that way. It's the answer 3. So then we might try another one here. Y equals log to the base 10 of 0.001, which is log to the base 10 of 1,000th. Can we write that as a power of 10? Yep, 1,000th is 1 over 10 cubed, or 10 to the neg 3. Remembering that negative power means 1 over. So now we've written it as base b and b to the x. So the answer is just the power. The log of a number is the power required to raise the base to get the number. So don't go too far away from that fundamental definition. Let's go down and have a look at your first set of exercises. So there we are. These are all manipulating the idea here of going between an exponential equation and a log equation and working them out generally without a calculator. So freeze the presentation there and have a go at these first 34, and the answers are down below. I'm going to scroll down there in a minute. And then we'll just display these others here. Questions 35 to 42. You use a calculator for these. Okay, so freeze the presentation at those various stages. Have a go. I'm going to go down now and look at the solutions. Okay, so we've got these in full now. There's the first 18. And you'll notice here they're saying, see, if you write 16 as 2 to the 4th, you have the answer there. The log of that will be the power each time. So try to write the thing you're trying to find the log of as a power of the base, and then the answer is just that power if the base is 2. So check that out. Okay, pause the presentation and mark your work. I'll go down and show each of these in turn then. So just the next batch down to perhaps 23 and 30. We can pause the presentation there and mark your work. And then we'll go down maybe 24 and 31 there. Just go down to that batch. And then from 34 through to 42. Alright, so have a go. Check that you're on track there with the fundamental definition. Let's move on then and have a look at example 10 here. Finding the domain. Perhaps we'll just go up so we can just see that. Oops, go back a bit now. Just this one. Find the domain of the function log base 2 of 4 take x squared. Now, you know the definition of the log is the power you raise the base to get the number. And b is a positive base. So what sort of powers would you expect to have to raise b to get a number? So here you could have any power. But what sort of numbers are powers of a positive base? So a positive base always can only be worked out, gives a positive. So therefore you can only find the log of a positive number, because when you raise b to any power you get a positive. So if you're asking what is the power you raise the base to get a positive, that's okay, but you can't find a power of a positive base you cannot find the log of a negative, because a positive base raised to any power will be positive. So what are we going to say? Here it is. Whatever's in here must be greater than 0. And you can't find the log of 0. There's no power of a positive base that comes to nothing. You might say, well, what about some negative powers? Oh yeah, negative 4 means 1 over b to the 4. So negative powers still only produce a positive number. So you only can find the log of a positive number. Therefore, over here, we're saying that if we're finding the log of 4 take x squared, 4 take x squared must be greater than 0. This must be greater than 0. And so when is 4 take x squared greater than 0? Well, I don't know, you might do it like this. Might be easier. Add x squared to both sides. So here x squared must be less than 4. So therefore, to get that, x must be less than what? X squared less than neg 4. It must be between neg 2 and 2, mustn't it? So here, when 2 is squared and bigger, it gives a number bigger than 4. Neg 2 squared, it is 4, so it's not outside there. You must have it x squared less than 4, so it's between neg 2 and 2. And or you could draw a sign diagram over here for that factored form between neg 2 and 2. Alright, so the domain requires that the value the expression you're finding the log of must be a positive. And does that link up? Yeah, that links up with our graph, which looks like that. So that here only positive x here can you find the log of. Alright, let's go on and see if we can use that now. Alright, so here we're going back to our function, our exponential function and our log function, and let's have a look at what we suspected before, that one was the inverse of the other. If you do the inverse of f to f, you should get x back again. Or if you do f on its inverse, you should get x back again. So let's do it. Now, let's say that's the inverse of our function. Let's just check it out. We'll do log to the base b of our function b to the x. Oh yes, log to the base b of b to the x is x. Now let's do our function to our proposed inverse. So there's b, and we'll raise it to our inverse, log to the base b, and from the definition, yes, it does give x. And so we start off with here, in our exponential function, we can put any x in. X is a member of R, but in our inverse function, x must be greater than 0 there. Okay, because we can't find the log of a negative number. We're using positive bases. When positive bases are raised to powers, they give positive numbers. There's no equivalent power of a base for a negative number. Okay, so what we're going to say now, we have proven it. If there we have an exponential function, then that is its inverse to the same base. So the function over here, y equals b to the x, reflected in the line y is equal to x, and you will have y equals log to the base b of x, interchanging x and y, and the function is another way of doing it. Do you want to do it that way? Let's take our function as f of x equals b to the x. First of all, let y equal b to the x. Then we're going to interchange x and y. Alright, remember this is our standard way of finding the inverse. And if x equals b to the y, that implies y is the power required to raise b to get x from our definition. So x equals b to the y means y equals log to the base b of x, and we always make our conclusion down the end. Therefore the inverse function is log to the base b of x. So if we start off with a function b to the x and we go through our inverse function procedure, then we do produce that inverse function. Alright, so let's go on and develop it a little bit more and do some more examples of what we can do here. So just coming down, example 11, evaluate the following expressions. Now here, this is still using the same rules here. The two rules, first of all, if y equals log to the base b of b to the x, the answer is the x. Also, if we raise here the base, let's say b raised to the log of, what can we say, the log to the base b of x, we will get x. So here we're raising b to the power of b needed to get x, it'll be x. So they're our definitions. Let's go through now. Log of 1/10 to the base 10, right, that is 10 to the neg 1, and so the log is a neg 1. Do the same thing here, log to the base 10, let's work out root 10 as a power of 10, there it is, so the answer is just a power. Log to the base 10 of 1, what do you raise 10 to get 1? It's 10 to the naught. So the log is 0. Here's the other definition. 10 raised to the log to the base 10 to get 47. You must get 47 by definition. And then doing some on the calculator, straight log to the base 10, LOG button, and do 3 decimal places. What's log to the base e of e? Well, e is e to the 1. So that's another one where log to the base e, and we've written the number as a power of e, it's e to the 1, it must be 1, our other definition. Log to the base e of 1 on e cubed is log to the base e of e to the neg 3. By definition, that's got to be the required power of e. Again, log to the base e of 1. Let's write 1 as a power of the base, it's e to the 0. Therefore, what is the power? We raise e2 to get 1, it's 0. And in e land again down here, e to the ln of 5, what does that mean? ln 5 means the power you raise e2 to get 5. And that's what we're doing, raising e to that, so we must have 5. And then in ln land, another calculator 1. So that's our first example there. And let's go on and see if we can look at a couple of other uses. Now, here we've got two curves, and we're suggesting that we're trying to connect these two, and if the curve A is a graph of log of x, log to the base 10 of x, which could be written like this. They're saying the curve B is the inverse because it's reflected in the line y is equal to x, and therefore what would curve B be? Well, we know the inverse of these two functions, 10 to the x has log to the base 10 of its inverse, and vice versa, so we can say that's over there. And so when x is 0, in there where it cuts the y-axis, we'd have 0, 1 in there, and over here would be what? 1, 0. And on this graph would be 10, 1. When x is 10, what's the log of 10 to the base 10? It's 1. So over on here, when x is, let's go across here, when x is 1, y would be 10. So they're the key points to match up on an exponential function and the log function, which is its inverse. Okay, so coming down, the properties of logs now. Let's go to level 2. If they're all powers, and we're talking about all positives in here now that we're working with, positive real numbers, a positive base, so we don't get any problems with whether the function actually exists there. So what's the log to the base b of two things times? Well, when you times two things, what do you do with their powers? You add them. So we're going to add the logs. The log of a product is the sum of the logs. So that's what it says here. And here's the equivalent rule in ordinary power land. The log of two things divided. Well, let's come over here. When you divide two numbers and they're both powers, what do you do with the powers? You subtract them. So if we're in log land, you will subtract the logs, because the logs are powers. The log of a quotient is the log of the top line minus bottom line, or numerator minus denominator. What about the log to any base of a number raised to a power? Well, hang on. If we have the log, we're writing that number as itself a power, then raising it to another power. What do you do with the two powers? You times them. So if you can powerize m, the log of m, get a power of the base, then you will times it by the other power. So the log of a number raised to an exponent is the exponent times the log of the number. Because when you get the log of a number, you're working with the power. The log is the power required to raise the base 2 to get the number. So you're really reflecting the power rules. All right, let's go down, and I'll just go through one of the proofs here. The three proofs, you can pause the presentation and look at it. I'm going to go through the first one here. So if you let x be the log of m and y be the log of n to some base, any base, it doesn't matter, then we can rearrange this. If x is the log of m, it's the power required to raise the base 2 to get m. And if y is the log of n, it's the power of the base to get n. So now, if we look at that, what's the log of the product? Well, it would be the log of b to the x by b to the y. And if you multiply those two together by the power rules, you get b to the x plus y. and so therefore the log is x plus y. But hang on, we said x was the log of m and y is the log of n. So we've just proven it, that the log of the product is the sum of those two pieces. Now in a similar way, Pearson's here have proven the other thing, so you might pause the presentation and have a look at that. Same idea, just watching how the power rules filter through to the things that we do with logarithms. Alright, let's go on now and have a look at some examples where we can use that. So each of these log expressions we're going to write as simple expressions. So let's have a look here. Log to the base 2 of two things times. So we know when two things are times, if you logarithm them, that's a good one. If you make them logs, you're looking at powers, so you will add the powers. And what is the log of 8? Power you raise 2 to get 8 is 3, so it can be simplified. What is the log L to ln, log to the base e of two things divided? You'll subtract their powers. Remember, the log means you're going to work with powers only. Log of root 7 is log of 7 to the half. So this is a half times log of 7. It's base 10 here, because we've just got those over here. We've just got log, so it means base 10. So we're going to write 7 as a base, as a power of 10. There it is. We're raising it to another power. What's the log to the base b of these two things divided? Log, or the power required to raise b2 to get the top line. Because we're dividing them, we'll take away the power of the bottom line. Now we can simplify that a bit more, because we've got x cubed. If log of x is a power of 10, we will multiply by that other power. Raising a power to the power, you multiply them together. And again, this one here. If we write y as a power of b by taking the log of it, there it is, and when we raise it to another power, we have to multiply that log power, the log of which is the power of b, by that other power. And so on we go. Two things multiplied, their sum of their logs, and then multiplying here by 2, and of course log to the base e of e, because e is e to the 1, that is just 1. So we can simplify it down quite a bit, and then you could put it on the calculator. Okay, let's look at the last one. The log of two things divided is therefore the sum of m plus n, take the log of m. Please notice that you cannot split log of m plus n up. You can't say it's a log of two things added, because that is the log of mn. If you add two powers, you're actually looking at the log of a product there. So come over here and just make sure when we're using f of x notation, it doesn't mean timesing. So what it means here, if you've got f of x plus y, then what that means is in place of x in the function, you put all of x plus y. So it's not going to equal f times x plus f times y. It's not that sort of thing at all. We saw that before. Log is not timesing in here. You can't do these two. You can't separate them. It's a symbol for a function like f is. So here, it isn't equal to the log of x plus the log of y. It says in the log function, put x plus y as a variable instead of replace x by that. Instead of log x, you put x plus y in there. So here it's important when you're dividing logs, you can't say it's that, can you? Because log of x over y, this thing is actually log of the top line minus the bottom. When you're dividing two numbers, you subtract their powers or their logs. And so here you cannot separate these to this either. Log of x to the k means you've actually got to raise this k times because of where the k is outside the bracket there. So you've actually got to do that k times if the k is outside there. Alright, so just watch the notation and some of the tricky little pieces there. Let's come down And have a look at another example. So here, can you go backwards? Okay, the log of 6 plus the log of x. We're adding two powers, therefore it's equivalent to the power of the product. This is the power rules in reverse. Log base 2 of 5 plus 2 times log base 2 of 3. So let's do this 2 log base 2 of 3 first. So we've got log base 2 of 5, and multiplying the log by a number means you're raising it to a power, because a log is a power and you're multiplying by 2, so 2 must also be a power. So you've now got log of 9. Adding logs is the log of two things times. Pearson's using that as multiplying. So it's log to the base 2 of 45. Subtraction of logs. Make sure they're always, the base is common. Base is the same for each of them. You can't combine them if they're using different bases. So we're subtracting logs. Logs are powers, so that when do you subtract powers? When the two things are divided. So let's go down to the next one. Base b of 12. Take a half log base b of 9. So log base b of 12. And you're multiplying here the log, which is a power, by a half. That must mean that half is behaving as a power. So it becomes log to the base b of 12. And 9 to the half is the root of 9. So it's log to the base b of 12. Take log to the base b. The root of 9 is 3. Subtraction logs. Subtracting powers. You will be dividing. So it's log to the base b of 4. Okay, log to the base 3 of m plus log to the base 3 of n. Take 2 log to the base 3 of p. Getting complicated now. So we added 2 logs. That will be the log of a product. We're then subtracting 2 times the log of p. That'll be the log of p squared. And now we're subtracting logs. That must be the log of a quotient. You subtract powers when you are dividing. And then the final one now is a subtraction of these two, which is the log of the division. Subtracting powers means you're doing a division. Log to the base 2 of 16. And what is 16? 16 is 4 squared. Oh, oops, no, I want to do that differently, don't I? It is 4 squared, but I want to write it as 2 to the 4th. So log to the base 2 of 16. What power do you raise 2 to get 16? Let's just come up here a little bit. And it's already written as a power. So it's 4. So that is the answer. Alright, so come down a bit. And we just had a quick look then. There are some questions. 46, 47, 48, 49. Please keep in mind the property of the log graph. Y equals log to the base b of x always passes through a couple of important points. Always passes through 1, 0, and also b1. Because just remember, b, the log of b, if log of 1 is always 0, right, the log of 1 will always be the power you raise b to, and b to the 0 is 1. Okay, so remember these points. The log to the base b of b is just the power of b, which is just 1. So there's a couple of important points to help you work out the formula of these functions here. Alright, so pause the presentation, have a go. I'm going to go down and then bring up the solutions after we look at the next set. Okay, the next set here, questions 50 to 61 there. Let's just come down a bit and have a look at those. I'll see if we can get it right in the middle here. 61. Yeah. Okay, so we've got two different types here. Here, slightly different steps required for each of these, as with the examples up above. You might need to go back and have a go at those. So let's then pause the presentation and see if you can unravel these, remembering the log is an exponent or a power. Therefore, adding logs will mean you're looking at the log of a product. Subtracting logs means you will be looking at the log of a quotient or two things divided. And multiplying the log of a number by another number means that other number must be a power, because otherwise you wouldn't multiply the log, which is a power, by another number unless it was a power raised to a power, that idea. Alright, so pause that and have a go. I'm going to go down and look at the solutions now. Alright, so here's the first little set here of the domain and ranges of these. So 43 onwards there, and coming then down to 52. And 54, 57 there. Just come down a bit. Down to 59. Yep, 60, I think we need to have a look at that a bit more closely. 60 there. And then 61. Okay, so you might like to toggle back and have a look at those problems and then mark your work. Alright, I'm going to go on now. And let's look at the change of base idea. In an earlier example, one of the answers was that. And you can work that out, because 2 to the 4th is 16. The answer is exactly 4. But what about something like, well, here we are. Example 13 was 2 plus ln 5, which was approximately that, using natural logs. But what if we wanted to work out an answer log to the base 2 of 45? There's no log to the base 2 button on the calculator. So how could you do that? So we need to look at a change of base formula. This is in the information booklet, this change of base formula, so you can look at it there as well. So we might try to relate log to the base 2 of something like 45. Can we use a conversion to log to the base 10 or log to the base e, because they are on the calculator? So let's go down and have a look. Here's the formula, and we'll put the proof up with it. So if you want to change, so here we're saying working with positive numbers again, so it makes the definition of the log function much easier. So they're all going to work out, in other words. And we're saying if you want to find log to the base b of x, then you could convert it to a base that you know. You first of all find log to the base, the known base a, let's say, of x, and then you divide by, let's say, a conversion factor, log to the base, that known base, of the converting base. So I'd like to put this in words. The log to a new base of a number. This is not a bad way of thinking about a generic mathematical formula, is log to the known base, if you like, of the number divided by log to the known base. There's like a converting factor in the bottom line of the new base, which isn't tabulated, if you like. So if you want some new log of a number to some wacko base there, all you have to do is find the log of a number to either of the bases on the calculator, base 10 or base e, and then, if you like, this is let's say a conversion factor, you're going to divide by log of that known base on the calculator to of the new base you're converting to. Let's look at the proof. So let's say we want the log to the base b of some number x. So what we need is y. So y is the power of b needed to get x. So we can just go to that from our definition. Now if we take log to the new base of both sides, log to the base a of x equals log to the base a of this side, log base a of b to the y, and therefore bringing that power down because it's raised to a power, multiplying the powers together. Log to the base a of x is y times log to the base a of b, and of course then we can divide both sides by log to the base a of b, and we have our result here of y being, what was y? That was log to the base b of x. I will just go back up again there and just check that. So here it is, log to the base b of x, which was what y stood for up here in the beginning, is log to the base a of x divided by log to the base a of b. So you can pause the presentation and just study that a bit if you'd like to. There's Pearson's explanation there. So we can actually find on our calculator the log to any base of any number by converting it to either base 10 or base e and using the calculator. Well, let's come down and have a look. Here's an example. Use the change of base formula and common or natural logarithms to evaluate each. So log to the base b of 30, what will you do? Go straight to the definition. It's log to the base 10 of 30 over log to the base 10 of our new base, the conversion factor. Okay, so we could do that. Pearson's is saying you could make an approximation, because 3 cubed is 27 and 3 to the 4th is 81. The value of log to the base 3 of 30 is somewhere between 3 and 4, closer to 3. Okay, and then you can check it on the calculator. Okay, so let's come down here for part B. Log to the base 9 of 6. Power you raise 9 to obtain 6. Let's do it. Log to the new base 9 of 6 is, let's go to use ln, that's on the calculator, is the log of the number divided by the conversion factor, log to the base e of the new base. So remember, the way to think about it is log to, let's call a new one, new base of some number is equal to log to a known base of the number, so that's base 10 or base e, over log to the known base of the new base, a conversion factor if you like. Okay, so that's the sort of pattern you need to think of when you see that change of base rule. Otherwise it looks quite complicated. Alright, let's come down. We've got some problems here for you. 62 to 65, and then 66 and 6 of 67, using those two to evaluate the common or evaluate the new log bases using log, which is common or base 10, or ln on the calculator. Okay, we'll have a go at those. Pause the presentation. You might have to rewind it to get the hang of that change of base rule. And then I'm going to go down now and look at the solutions to those up to 70. So let's have a look now. So there are some of them there, still a couple down the bottom I think. So pause the presentation and check your answer there. Let's go down and look at those last couple down to 66, 67. Pause that and check your answer. So we're going well with understanding this log function, all the things that we can do with it. There's a couple of other exciting things coming up. So check your work. I'm going to go on now. So coming down with me there, solving log equations, and so this is where we're going to end there. And when you have the log equation, you can always remember if y is the log, then it's the power of the base. There it is there. So these are equivalent forms, remembering the log of a number is equivalent to the power of the base. So when some statement says it is the log, then it has to be made the power of the base. Log is equivalent to a power. Okay, and some of the other things you might look to, you can read Pearson's, I'm abbreviating it here. If A is equal to B, we've said this from exponential equations, if you have the same base on each side, then n to the A will equal n to the B. Also, IB loved this definition, B raised to the log of x, if it's base b there, is just got to be x. Again, according to the definition. The log to the base b of x is the power necessary to raise b to get x. And we have done it. So you must get x back again here. And so the logarithm is an exponent. Here Pearson's saying it. So let's just come down a little bit, have a look at this. Log of x equals 4. Hey, 4 is the log. 4 is the log to the base e of x. Means when you find x, it must be e to the 4th. Or we could say e to the ln x means e to the ln x would be e to the 4th, and do it that way. I prefer you go straight from here to here. Use the definition. The log is 4. Oh, and it's base e, so therefore x is e to the 4th. I don't think we need the middle term in there. Just go straight from the definition. So think about that. Let's come down and look at some here now. Some examples. Log to the base 3 of 2x take 5 is 2. What does that mean? The log is 2. It means that is the power of 3. So to get 2x take 5, you raise 3 to the 2 or get 9. We can come, I think, straight to this step here, realising that the log of base 3 of 2x take 5, so you're trying to work with this number, and its log to the base 3 is 2. So that means you go straight to 3 to the 2. Alright, what about this one down here? Log to the base 2 of phi to the x. What does that mean? It's equal to 3 plus k. It says the log is 3 plus k to base 2. So let's raise base 2 to the 3 plus k. And you must get 5x then, if you're raising it to that power. So just come back and let's get rid of that flip there. So here then, the final bit of that one. It doesn't want to go there, does it? So let's come here like this then. So here we say 5x is equal to 2 to the 3 plus k. So I'd rather you went straight to the number is that power of the base, because they said 3 plus k was the log. And then of course we can split it up and then write it 8 there. So 8 dividing here, dividing by 5, 8 over 5, 2 to the k. So we can play around there quite a bit. I think going straight from the definition, if you know that the log of something is given, the log of 5x is given, that goes straight into Powerland. And so you can say 5x straight away is that. Alright, come down and have a look at, I think, just one more, and just checking here. So here, the sum of two logs to base 2 is 4. So here, let's simplify this side. If we're adding two logs, we're looking at the log of a product is 4. Now, the log to the base 2 is 4. Therefore, 2 to the 4th is the answer to the number. Okay, go straight there. It says the log of this number is 4. So 4 goes straight up into the power of the base. And then we can rearrange this. What we've done here is put all terms actually positive x squared, moving it over there, neg 10x, moving it over there, plus 16 equals 0. We can factorise that and then say x is 2 or x is 8. So combining those two log expressions, remember the sum of two logs is the log of a product. Okay, you should be careful though to make sure that the two answers both work. So you should substitute these back and make sure that you can find the log of 2 in that hole and in this hole, and also 8 in both places, because sometimes we generate what's called extraneous solutions, and we'll have a look at that in this next example. Okay, so what about this? The sum of two logs again is 2 ln x. Let's look at the left hand side. So we're adding two logs, so that's the log of the two things times. And it's 2 times the log here. We're multiplying a power, a log, by a number, so it's the log of x squared. And so we can say the log of all of this equals the log of x squared. I would leave this line out. If the two logs are equal, the numbers are equal. Okay, the power you raise 2 to get e2 to get that side is the same as this side, so therefore the sides are equal. Putting all terms on the left, we get this equation. Factorising it, x is 6 or x is 1. However, there is a problem that if you sub 1 back in here, log of 1 take 2 is the log of neg 1. We know we can't find the log of a negative number. And if we put 1 in here for x, it's 2 take 3, which is neg 1. We can't find the log of that. So that is an extraneous solution. We can't include that. If we check x is 6 in this position, it's a log of 4 and the log of 9. So that is valid, and we can therefore have only one solution, x equals 6. Alright, so don't forget, in these bigger log expressions, log equations, where you have two log expressions equal to something or equal to another log, check your solutions for validity at the end, whether they're valid solutions. Okay, and you can do that with a graph here. So here you could have actually drawn the graph. See this here? We could have said, let's move all terms across to the left, put it on the calculator and find where it cuts the x-intercepts, or find the x-intercepts. So I've done this down here. You actually graph this function. So instead of solving that equation, put all terms across to the left and made this equation, which is saying when does this function here cross the x-axis. So I put in the calculator and done Shift F5 on the Casio for gsolve, and solve for the root where it crosses the x-axis and found only 6. And you can see the graph goes up and down there. You can't have the value 1, and the reason for that is it doesn't go down that far. Right? If you trace that back, it's actually asymptotic to a value before that. Okay, so that's another possibility to check that your answers make sense using the graph mode. That's if you're in paper 2, of course. If you're in paper 1, you won't have that calculator to use. Alright, so let's have a look at these problems now. The questions 22 to 32, solving some exponential equations. Remembering the rules. Adding logs is adding power, so that's a log of a product. Subtraction of logs is subtracting powers, that's a log of a quotient or two things divided. And then just your basic power raised to a power rule. Okay, so the log of a number raised to a power is the power times the log of a number. Just remember that one now. So let's pause it there. I'll just take this up a bit again. Hang on. Just come down here. And we'll pause it there. Have a go at those few problems there. What is it? 10 of them here. And then I'll show you the solutions. Right, so coming down to look at the solutions now. Down to 22 through 29 there. Just check your answers. Pause the presentation and have a look at them. And then we've got 30 and 31 just down below here. Just gradually bring it up. Oh, we've got 32 there. So having a look at that then, and having a go. Alright, so mark your work. Maybe go back and check some of the examples so that you can be sure you've got a good understanding. Let's go on to the final bit now. And up there 32, I'll just leave that there. I didn't realise 32 went on. And let's have a look at the practice problems now. There are 15 of these. Now these practice problems come from chapter 4 of Pearson's, and it involves both the exponential function, that earlier presentation introducing logs, and this logarithmic function presentation. So pause it there and have a go. This goes back to the exponentials. Or you might like to go on now and have a look at some of the others. We've got 15 of them. So we're starting to get more into the logs after question 7, I think. So pause it there. Or then into 11 through 13, starting to get into more logs there. Bit of a mixed bag. So you could pause it there. And the last couple, 14 and 15. So pause the presentation and try to work through those problems. I'm going to go down to the solutions now. Okay, so the fully worked solutions, fairly long here. Question 1, you could pause that. Let's go complete screen for question 2. Okay. And a little bit more there, the rest of question 2. Let's go down to question 3. Part of 4 there. And pause that. Okay, just bring 5 up. Okay, let's complete 5 there. Let's have a look at 6 then. 6 and 7. We look at 7. 8. I'm down to 9 now. 9 and 10 I think we can fit on there. 11. 12, 13. Let's go up a bit there. Just come down here. 14. And then down to 15. Alright, so a number of problems there. Good to catch up with those practice ones for revision. And good on you for coming so far. You're building up a lot of skills. It's really good. I hope you're enjoying it and feeling really empowered in handling some of these more complicated stuff now in the exponential and log areas of mathematics. Well, that's the end of the presentation on logarithms. Very important functions, the exponential logarithmic functions in this course. We'll see them again a bit later on. But it's for now, it's cheers from me. Look forward to catching you in the next presentation.